So what does pH have to do with a shampoo? If we take a look at a somewhat related structure, this being the structure of Kevlar, but it is somewhat related to what the structure of hair is, we notice the presence of nitrogen or amine groups in hair and the presence of OH groups from the acid of organic acids. So hair is essentially a long chain molecule containing both acid and base groups in it. And if we wash our hair in solutions that are somewhat more acidic or basic in nature, we can alter the chemistry of our hair and as a result make it too brittle perhaps, or dry it out. So the manufacturers of shampoo try to balance the pH of their shampoo so it doesn't alter the structure of our hair. So today's lesson is a look at pH. We'll begin by looking at water. If we go back to Arrhenius's initial vision of water, he thought it as essentially a molecule that broke apart, and that can be represented by this equation. And it broke apart into an acid particle and a base particle. I'm going to write down the equilibrium law expression for this reaction, where I put the products on the top and the reactants on the bottom. A little note here about the substance on the bottom, water. The concentration of water in water is essentially a constant. So I can bring it up and combine it with the equilibrium constant. And that then will result in a new equilibrium constant. And that we call the ionization constant for water. Now Bronsted and Lowry had a slightly different view of what happens in water. One water molecule will bond to another by means of a hydrogen bond, and that hydrogen bond at times could become strong enough to actually remove the hydrogen. And in that case, we actually have a reaction between two molecules of water instead of one. One of the water molecules acts as an acid, the other is a base. Amphiprotic was the word we used to describe this. And again, I can write the equilibrium expression for this reaction. And again, the concentration of water in water is essentially a constant. So I can combine it with the equilibrium constant to come up with the equilibrium constant for water. It's called the ionization constant. Now, this is a very, very small number. When water molecules collide, only a very small fraction of them actually undergo this reaction. And this information is available in your IB data booklet. I've shown it to you here. First thing you'll notice is the constant is affected by temperature. As my temperature increases, the value of the equilibrium constant increases. That suggests then the addition of heat is shifting the reaction to the right. That would then happen only if the energy term was a reactant. So the ionization of water is actually an endothermic reaction, requires heat to proceed forward. I want to focus in at one temperature, 25 degrees Celsius here, and the equilibrium constant that's associated with it, 1 times 10 to the minus 14. We're going to use that in our next example. Let's consider a liter of water at 25 degrees Celsius. If we use the simple expression for breaking down water, I've written the reaction, the water molecule breaking apart into a hydrogen and a hydroxide. Now, initially the concentration of water in water. That I arrive at by determining the number of moles of water in a liter. So a kilogram of water, which is a liter of water, divided by 18 gives me the moles of water over 1 liter. So the concentration of water in water is around 55.6 moles per liter. And initially I don't have any of the ions present. After a short period of time, a certain number of the water molecules break apart and the concentrations of my two ions both go up by the same amount. And finally at equilibrium then, I have X and X is the concentration of my acid particle and base particle. Now I'm going to go and grab the equilibrium expression for water and substitute those values in. And again, I'm using 25 degrees Celsius, so I know the constant is 1 times 10 to the minus 14. Solving then for X, I get 1 times 10 to the minus 7. So that means the concentration of my acid particle and the concentration of my base particle are 1 times 10 to the minus 7 moles per liter. Essentially, they're both equal, and that's why water is neutral. It's because the number of acid and base particles present in water at 25 degrees Celsius is essentially equal, and that's what makes water neutral. Now let's take a look at what's meant by the pH. pH essentially focuses on one of these particles. It focuses on the acid particle, so you can view it as either the hydrogen ion or the hydronium ion. By definition, it's the negative log of the concentration of the acid particle. Let's look at how this works. I'm going to go to my first example where the concentration of the acid particle was 1 times 10 to the minus 7. Now the log of this is minus 7, and the negative log of this is 7. So the pH of my water is 7. In my next example, if the concentration of my acid particle was 0.001, that's the same as 1 times 10 to the minus 3. So the pH would then be 3. Now the next one, I'm sorry there is no shortcut. We'd have to probably put this right into our calculator and then take the negative log of that number, and I get 1.3. Let's try a few going in the other direction, where you have the pH and you want to know what the acid particle concentration is. Well, if my pH is 11, that means that the concentration then of my acid particle would be 10 to the minus 11. Similarly, if the pH is 5.6, then that means the concentration of the acid particle would be 10 to the negative 5.6, or 2.5 times 10 to the minus 6. And lastly, a pH of minus 1. Yes, you can have negative pH values. That means it would be 10 to the negative 1, or 10 moles per liter. The pH and the hydrogen ion concentration are essentially inversely related to each other. If you look at my particular example, you can see the concentration of the acid particle was increasing, and the pH was actually decreasing. So as one goes up, the other goes down. The other thing you should note is the pH scale is logarithmic in scale, meaning a 1 unit change in pH constitutes a 10 times or 10-fold change in the concentration of the acid particle. Let's try a couple of examples. So I'd like to determine the acid particle, the base particle, and the pH of a 0.01 mole per liter solution of nitric acid. Now the first thing you should note is nitric acid is a strong acid, so that means that when it's placed in water, it dissociates or breaks apart 100%. So I can say then that the concentration of the hydrogen ion, which comes from my hydrogen nitrate dissociated, will be the same, 0.01 moles per liter. And that's the same as 10 to the minus 2. If I now look at pH, pH is the negative log of that number, so the pH itself would be 2. Now lastly, to get the concentration of the base particle, I go back to the equilibrium expression for water, that the product of those two ions will be 10 to the minus 14. Well, I already know the concentration of one of them, the acid particle, so I'll substitute that expression in, and then isolate for the concentration of the hydroxide particle, and I get 10 to the minus 12 moles per liter. Just a note here that this is an acidic solution, and you can see that because the concentration of the acid particle, 10 to the minus 2, is much bigger than the concentration of the base particle, which is 10 to the minus 14. That's what makes the solution acidic. Let's try another example, but this time we'll try a base. You've been asked to prepare 500 milliliters of a basic solution of sodium hydroxide, and you want the pH to be 12.5. So how many grams do you need of sodium hydroxide to do this? I'm going to begin with the pH. With knowledge of the pH, I know what the concentration of the hydrogen ion is. It's 10 to the negative 12.5. Knowing that this solution is in water, I then apply the ionization constant for water, knowing that the product of the two ions is 10 to the minus 14, so I can substitute in for one of them, and thereby solve for the concentration of the base particle, 10 to the minus 1.5. I can take that and put that in the calculator to get 0.0316 moles per liter. Now that's the concentration of the OH ion. But there's one OH in every sodium hydroxide. And because sodium hydroxide is a strong base, I can say that the concentration of the OH is the same as the concentration of the sodium hydroxide. So I now know the concentration of the sodium hydroxide. I also know the volume, so I can calculate the number of moles and hence the mass. So you can see that here. I determine the mass by going concentration times volume times molar mass. And I get 0.063 grams required. So I hope that this has helped you out with an introduction to what pH is and how it's related to the concentration of the base particle. And again, if you find these programs useful, let me know, and comments are always welcome. Thanks.